So, good afternoon, everyone, and welcome to today's lecture. This is Thermodynamics lecture number 3, and I guess we should be able to wrap up this topic by today. In the previous lecture, I think we had seen the two processes. The first of them was isothermal, and the second one was adiabatic. Do we remember those two processes? Isothermal and adiabatic process. And I had shown it to you that both the process are actually the opposite of each other. Why they are the opposite of each other? Can anyone tell me what are the conditions that are required for a process to be isothermal, and what are the conditions required for a process to be adiabatic? Yes,
For isothermal, walls of the container must be perfectly
perfectly,
conducting, sir.
and the process must
Must
take
be
place
slow.
very slowly, so that there is adequate time available for heat exchange to take place, right? So it's a very slow process, and that takes place in a perfectly conducting environment. Did we discuss free expansion? Did we express the process of free expansion?
Sir.
Yes or no?
No, sir.
Okay, then we can start today's class, because this is a type of adiabatic process only, and we call it the process of free expansion. Now, what do you mean by this process of free expansion? Now, in this process of free expansion, what happens is you have a chamber, you have a chamber in which this process takes place. This chamber is insulated, and you have one piston in this, and we have a gas here at pressure P1, volume V1, and temperature T1. And this side you have something known as a vacuum. This side there is nothing but vacuum. Now remember, whenever we talked about work done by the gas, now work done by the gas, we have seen it as it is an integral of P dV, but I think I have told you that P, that pressure that we are talking about in work done, is the external pressure and not the internal pressure. Do we remember it? Yes or no? Yes or no?
Yes, sir.
So here the external pressure, because this side there is vacuum, so this external pressure here is zero because there is no pressure on the other side. So the as soon as you leave this piston, this piston will rush on the other side. This piston will rush on the other side, and in this process you must understand that there is no heat given, there is no change in internal energy, and there is no work done. Why there is no work done? Because on the other side we have vacuum. So this process is known as free expansion, and you can call this process, because this is going to take place very fast, you can call this process as adiabatic process. This is known as the process of free expansion. I'll give you 1 minute to note it down. We will now move on to the third type of process, which normally I do as the first process. The third type of process is known as isochoric process. Sometimes you may also call it isometric process. What is an isochoric or isometric process? As the name suggests, this is a process where not the volume is zero. Here the change in the volume is zero. The change in the volume is zero. So volume remains constant in this process. The volume remains constant in this process. This process is known as isochoric or an isometric process. Do we understand this? Yes or no? It's the simplest type of process, and we have done a couple of questions on this as well. Do we remember this?
Yes, sir.
Now, talk about the equation of state for this process. As you can see, first listen to what I'm saying and then I will give you time to note it down. Now, if you look at the equation of state, PV is equal to nRT. It is always valid for a ideal gas. Here N will remain constant, R will remain constant, V is constant. So the process here becomes, please note, please first listen to me, then I will give you time to note down. P1 by T1 will be equal to P2 by T2. Do we understand this? Yes or no?
Sir.
Okay. First, listen to me and then I will give you time to note it down. First, listen to me. Okay. The second thing that you must understand is the indicator diagram. Whenever I say indicator diagram, it means that the diagram of P versus V, and you can see the diagram of P versus V. In this case, it would be a straight line which is parallel to the y axis. Yes or no? The PV graph would be a straight line which is parallel to your y-axis, and you can see there is no change in volume, so the work done under this process will be zero. Do we understand this? Yes or no?
Yes, sir.
One more thing I will tell you. Now remember, for every process we will have some specific heat. Some specific heat. Now the specific heat for this process is known as molar heat capacity at constant volume CV, and we have seen the value of CV is F by 2R. Do we remember this? Yes or no? Okay, so now I will give you time. Note down everything. Remember, for each and every process we have specific heat. For an isothermal process, the specific heat was very large, infinite. For an adiabatic process, specific heat capacity was zero. For isochoric process, the specific heat is known as CV, and CV is always F by 2R. We all remember this, yes or no?
Yes, sir.
Now I'll give you 2 minutes. Note it down. And once you are done, please let me know. Okay, then we move on to the next point. And remember, we are
Sir,
doing
1 minute, sir.
it in the same order. Yes, what happened, beta?
Sir, 1 minute, sir. Noting down.
The next point is the next point that you have to see is bulk modulus, and I have kept the screen on the same thing, so if you have not noted it down, you can note it down. Bulk modulus of elasticity. Remember, for different process, the bulk modulus of elasticity is different. Now this question can come in your JEE Main or as well as your NEET. So please remember, bulk modulus of elasticity for this process is infinite. It's infinite. I hope you understand this, because delta V change in volume is zero. Now I've already told you that work done in an isochoric process is zero, because there is no change in volume, so the work done would be zero. Anyone understands this? Yes or no? No, yes. Anyone understands this? Then
Yes,
if you
sir.
apply
Yes, sir.
the first law of thermodynamics for this process, you will have delta Q is equal to delta U plus delta W, but delta W is zero. So your delta Q becomes delta U, and that becomes N CV delta T. Delta Q for this process is same as delta U, and that becomes equal to NCV delta T. Everyone understands this? Yes or no? No, yes.
Yes, sir. Yes, sir.
Okay, I'll give you 2 minutes to note this down, then we'll solve some problems on the same. 2 minutes. Let me know once you are done, once everyone is done. So here is a question for you. Based on the process, find out the change in internal energy for this process. and I'll wait for your answers. 5 moles of oxygen is heated at constant volume from 10 degrees Celsius to 20 degrees Celsius. What will be the change in internal energy? The specific heat is given as 8 calorie per mole. Cp is given, R is given. I think you should be able to find out. Remember the value of R in calorie per mole. The value of R in calorie per mole is actually 2. So remember this. They will give you in any case, but you can remember it like this. So I'll give you 2 minutes to give me the answer. So how are you supposed to do this? It's a very simple question.
minus C,
U
C is equal to R, sir.
is equal to delta U is equal to N CV delta T. I just put the values. N is 5. CV is how much? 8 minus 2.
6, sir.
Multiplied by change in temperature is 10 degrees. The answer is simply 300 calories. That is the answer that I was looking at. Do we understand this? Yes or no? No, yes?
Yes, sir.
Yes, sir.
Now, remember some examples of this isochoric process. Wherever you have the volume remaining constant, the process becomes isochoric. So, remember, no one is going to ask you the examples of isochoric process. But if you see such processes where the volume remains constant, there is no moving piston anywhere. The process is taking place in a cylinder which is closed and closed from everywhere. You can understand that these are the examples of an isochoric process where the volume is going to remain constant. So you can note down these cases of isochoric process. You may get one of this as a question and you may just remember case number 1, a gas enclosed in a vessel, no moving part. Number 2, when a substance melts, you can take it as an isochoric process because the change in volume is very, very less. Number 3, heating of something in a pressure cooker is an isochoric process as well. So you can note down these examples as examples of isochoric process. Remember, there is no change in volume, there is no moving part, there is no piston, nothing of that nature. I'll give you 2 minutes to do this. Let me know once you are done. Then let's move on to the next process. After isochoric comes the next one. What is the next one?
Isobaric.
Isobaric or constant volume process. Isobaric process. Here, the pressure remains constant. Here, the pressure remains constant. Isobaric process is a process where pressure is going to remain constant. Everyone knows this, yes or no? Isobaric process is the process where the pressure remains constant. Now, if the pressure remains constant, first listen to what I'm saying and then I will give you time to note it down. If the pressure remains constant, then the equation of the state would be very simple. Volume will be directly proportional to temperature. Remember, absolute temperature, we are talking about V1 by T1 will be equal to V2 by T2. We understand this? Yes or no? No or yes? We understand this, everyone? V1 by T1 will be equal to V2 by T2. That is the first thing that you should understand. Then the second thing that you should understand is how the PV graph or the indicator diagram. Remember, when anyone uses the term indicator diagram, the only thing that should come into your mind is that it is a PV graph. And in this case, the PV graph of this gentleman, and why it is not coming? The PV graph of this gentleman is a straight line. Oops, what has happened? Something. Okay, I think it got stuck. Okay, not a problem. I'll do it again. Okay, so you must understand that the PV graph for this will be a straight line which will be parallel to your which axis?
Exactly, sir.
It will be parallel to your x-axis. That is absolutely correct. And the slope of this PV graph is going to be 0. You can very easily find out the area under this graph. The area under this graph will give you work done. Yes or no? No, yes.
Yes, sir.
Okay, the specific heat, the last point here, the specific heat for this process will be known by the name of what? The specific heat for this process will be known by the name of Cp. Yes or no?
Yes, sir.
So the specific heat for this process will be known by the name of Cp, and the value of this Cp will be equal to F by 2 plus 1 times R. Everyone knows this? Yes or no? It comes on your screen now. And this is giving me some trouble. So I'll give you 2 minutes to note it down. Can everyone note it down now? The specific heat for this process. I'll give you 2 minutes to note it down, draw the graph, everything. Let us move on to the next point. We have seen the 3 points. The next point would be, what would be the next point? We would have to find out the bulk modulus of elasticity in this case. Can anyone tell me what will be the bulk modulus of elasticity in this case?
0, sir.
Well done. See, now you are getting in the groove. That is correct. The bulk modulus for elasticity in this process is going to be 0. Well done. So if you understood the concept, that is what I wanted. The next thing is the work done in this process, and you can write it in different forms. You can write it as P into V2 minus V1, or you can also write it as NR into T2 minus T1, or NR into delta T. Do we understand this? Yes or no? No, yes. The next
Sure.
point is the application of FLTD. Now, if I apply FLTD here, what will I get? Delta Q. Please first understand what I'm writing, then I will give you time to write it. Delta Q is equal to delta U plus delta W. Now remember, for any process, for every process, I can write the value of delta Q. Delta Q for this process can be written as NCP delta T. Yes or no? No, yes.
Yes,
Do we
sir.
understand this, or is it going above our heads? Huh?
Understood, sir.
Delta U for any process can be written as what? NCV delta T. Yes or no? And here, work done. Instead of writing it as P into delta V, I am writing it as NR into delta T. Now you will see how do you get that revolutionary equation, the Mayer's equation. Cp is equal to Cv plus R. You can derive this from these conditions. Do we understand this? Or
Yes,
is it
sir.
gonna saying bye bye, bye bye, bye bye? Huh?
Understood, sir.
Now I'll give you 2 minutes. Note this down. Aram se. Now we move ahead. Now we move to that question which actually came in your JEE Advanced, and every time I gave the example of this process. Do you remember that question that I showed you? That in that boiling process, you have to find out the change in internal energy. Do you remember that question? Huh? Anyone? And we had done that at that point in time also. This one. This one. Do you remember this question number 1 from JEE Advanced? So that, and we did it. Yes or no?
Yes, sir. Yes, sir. Yes, sir.
Normally, I discussed this question at this point in time, and I discussed both the processes. We have seen the melting process is an isochoric process. Yes or no? Yes or no? But the boiling process is an isobaric process. So the example of isobaric process is conversion of water into water vapor. And what they are going to ask you, is what is the change in internal energy. That was the same question that was asked here. Now you know how to find out the change in internal energy here. Yes or no? You can find out the change in internal energy, and you can do it by this fashion. You know this delta Q is equal to M into L, where M is the mass and L is the latent heat. Yes or no? You understand this? Yes or no? What I have
Yes,
done
sir.
here? Same thing we did in that question and we got the answer. Do we understand this?
Yes, sir.
And just wait, don't write anything now. I'll give you time. Now, if you compare this process with the process of conversion of ice into water, the process of conversion of ice into water is taken as an isochoric process, because there is very less change in the volume. So this process is taken as an isochoric process. Now, if I do the same thing for this process, since there is no work done in this process, which process I am talking about? I am talking about melting. There is no work done here because there is no change in your volume. The change in volume is very less. So for this isochoric process, the change in potential energy or the change in internal energy of the water or ice, whatever you are talking about, is simply equal to M into L, whereas in the other process it is M into L minus P into delta V. Do we understand this? It has gone above our head saying bye bye. सर निकल गया है तो निकल गया.
Aye, sir.
So this is this is 0 here because the change in volume between water and ice or water is very, 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 very small. We understand this? Now I will give you 2 minutes to note it down. Okay, then we move ahead in life, because the only thing that we can do in life is to move ahead. And this is the question. Remember, we have done a lot of questions on constant pressure process. This is just to revive our memory. And this is the first one. 5 moles of hydrogen gas is heated from something to something. Find out the change in something to something, whatever it is. Tell me the answer for this one. Do it fast so that I can move on to the next question. 2 minutes you have to show me your talents. So, how are you supposed to solve this question? Heat given to the gas. How do you find out heat given to the gas? Option A, B, or C. So, oops, I've changed the color. It's not coming. What is the heat given to the gas in this process? That is simply equal to NCP delta T. N is given as 5. Cp, you can find it out upon gamma minus 1 into the value of R. Now the color has changed. And this thing is giving me trouble. Okay, into R into change in temperature. What is gamma for this gas? This is a diatomic gas, yes or no? So it is 7 by 5 divided by 7 by 5 minus 1 into R, and the value of R is given as 2 into 2 into change in temperature is 30 degrees, and I think the answer that you are going to get is 1030. Anyone got this answer? Yes or no?
Yes, sir.
Everyone? Boys, I'm not getting anything from your side. Do we understand this?
Yes, sir.
How did you get 750, sir?
In case of CB, I tell CV, sir.
Why you take CV?
Perfect.
Stay in this universe. In this universe, the heat given in constant process is given by constant pressure process is given by NCP delta T. Do not wander in other universe. This universe is good, beta. You understand this, na? It's a good universe. Okay, so remaining in the same universe, this is the type of question I have seen it coming many times. When an ideal gas gamma 5/3, which gas is this? Mono, di, tri, what? Eh?
Die, sir. Mono, sir.
Open your eyes, take a deep breath. 4% of the universe, it's what you see. 96% we don't see. But it's a good universe to live in. Where 5/3 is the gamma for a monoatomic gas. When an ideal gas gamma is 5/3 is heated under constant pressure, what percentage of given heat energy will be utilized in doing external work? And you have 2 minutes to give me the answer and stay happy. But it's good that you got the answer. 40%. How you are supposed to do this? So what we have to find out? You have to find out the work done by heat given ka ratio. And how do you find out? You can write work divided by delta Q. And it is simple after this. So this basically will become your Cp minus Cv divided by Cp. Yes or no? Huh?
Yes, sir.
Just put the values, get the answer. And I think you will get the answer as 2/5. This will be coming as 2/5. Yes or no? So if I find it out in terms of percentage, the percentage that will come up is 40%. Yes or no? No or yes?
Yes, sir.
Okay. Now, as you can see, this is the question that I normally do in the class, and now it is not coming. So what I got to do is I will just close this gentleman and I will try to open it up again. It's got stuck somewhere. It's got stuck somewhere. So yes, it has got stuck somewhere. So just give me time. Well, the life moves on with this particular question, and the same question I have done in all my classes before. And you can see there is a striking similarity between this question and the question that eventually came in last year's JEE. I've been repeating this question many times. I'll give you a chance to do this. At 100 degrees Celsius, the volume of 1 kg of water is this. The volume of 1 kg of steam is this. The latent heat of steam is this. The normal pressure is this. 5 kg of water at 100 degrees Celsius is converted into steam. What is the increase in the internal energy of the process? I have already shown you how this question is done. I'll give you this as a practice. You have 2 minutes to give me the answer. Okay. So how are we supposed to do this? First of all, we will find out the work done in this process. Work done in this process will be P into dV. The pressure is given as 10 raised to the power 5. Change in volume. How much is the change in volume? The volume here is 1.67 and the volume of 1 kg of water is 10 raised to the power of -3. I hope we understand this. Yes or no? And you have 5 kgs of water. So 5 multiplied by, let me just write here in this. So the pressure is 10 raised to the power 5 multiplied by what is the change in volume 1.671 minus 10 raised to the power of -3. I multiplied it by 5 because this is 5 kg of water. So I will multiply this and I think you will get 0.835. I'm just noting down from the answers that I have. Delta Q, the heat given in this process, is M into L. Just have to multiply mass by L. 5 multiplied by 2.3 into 10 raised to the power 6. So that will give you 11.5 into 10 raised to the power of 6 joules. From here, you can find out the change in internal energy, delta Q minus delta W, but all just multiplying this. And the answer that you will end up is this one. That is the answer that we are looking at. I'll give you 2 minutes to note it down. So, bacha, here comes this question. It's a simple question and I want you to solve it and give me the answer quickly. A sample of ideal gas, F is 5, F degrees of freedom is 5, is heated at a constant pressure. The amount of, if an amount of 140 joules of heat is supplied to the gas, what is the change in internal energy and what is the work done by the gas? Remember, the concept is similar. They may ask you question in this way or that way, but the concept remains same. I'll give you 2 minutes to solve this. Great. So we got the answer for work done. Work done is definitely 40 joules. And once you get the answer for work done, the rest of the part is pretty damn simple because one is 40 joules, the other one has to be 100 joules. How did you get it? Yes. Tell me. No one knows it, how to do this? There are 10,000 different ways in which you could have done this. 10,000 different ways. So I'll tell you one of those ways. Delta Q is N into Cp into delta T. For this, degrees of freedom is 5. So you can find out the value of F. From the value of F, you can find out the value of Cp. Cp will be 7 by 5. Yes or no?
Sir.
7 by 5 into delta T. Delta Q is this much. What is delta U? Delta U for any process is always equal to N.
Delta T.
That will become N into 7 by 5. How did I write 7 by 5? 7 by 2 I should have written, right? Not 7 by 5. No, 7 by 5 I would have written. 7 by 2 I should have written. I'm also confused. Then NCV. CV for this will be 5
by
2 delta T. From here you can find out delta U. Delta U, and this is the same question that we did. Delta U. You can find out delta U. Delta U will be equal to delta Q into 5 by 7. Yes or no?
Sir.
You can get the value of delta U as 100 joules. As soon as you get the value of delta U, you can find out the value of delta W, and delta W will be 40 joules. Anyone understands this, or this has gone above it saying bye bye? Sir, I'm going bye bye, bye bye, bye bye, bye bye.
Understood, sir.
Good. Anyone understands this? Then we will move ahead. We'll move ahead and do one more process. The fifth one or the sixth one, whatever it is. I think it is the fifth one. It's known as a polytropic process. Now, what do you mean by this polytropic process? Anyone, any idea? Get idea? No idea? How do you, what is this polytropic process? Now we have seen isothermal, we have seen adiabatic, we have seen isobaric, we have seen isochoric. The only type of process that remains is this, which is known as a polytropic process. Now any process of this form, PV raised to the power eta is constant. This process is known as a polytropic process. Remember here, eta should not be equal to 1, because if eta is equal to 1, it becomes an isothermal process. Eta should not be equal to 1, then it is not valid. Because if eta is 1, PV is constant, it becomes an isothermal process. Eta should not be equal to 1. This process, and remember, eta should be a constant. It should not vary. It could be any number, any integer, any fraction, any real number, not imaginary, obviously. Eta could be anything, 0, 1, not 0 and 1. Not 0 and 1, because if it is 0, then the P is constant, it becomes an isobaric process. Okay, so eta could be anything. 2, 3, 1 by 2, minus 1 by 2, 3 by 2, this, that, thing, anything. Now, whenever you encounter these polytropic process, every process, whether it's polytropic or adiabatic or anything, will have a specific molar specific heat. Every process will have work done, and every process will have change in internal energy. Now, if I talk about the change in internal energy for this process, if it undergoes a process, how will you find the change in internal energy for this process? Yes, that is the first question that is coming up. How do you find the change in internal energy for this process? Polytropic process is what I'm talking about. How do you find out the change in internal energy for this process? Yes. How do I find the change in internal energy for this process? Yes? Any idea? Are? How will I find the change in internal energy for this polytropic process?
No idea, sir.
You have idea. The problem is you don't use your brains. What was the change in internal energy for an isobaric process?
NC delta T, sir.
Adiabatic process? What was the change in internal energy for an adiabatic process?
NCP delta T, sir.
N
CP delta T.
wow, NCP delta T. Yeah. Anyone with a different opinion about change in internal energy? In an isobaric process, what was the change in internal energy? Okay. Everything seems to have been confused. Anyone can tell me what is the change in internal energy in any process? Anyone remembers it? Okay. This is a big shock for me that after doing all these processes and I was about to finish this chapter and I ask you what is the change in internal energy and I get all sorts of answers.
NCP delta T, sir.
Pakka?
Yes, sir.
What is the change in internal energy? Oh God, this is too much. Oh God. Yes, I'm still waiting for the answer, actually. I've not given up still.
NR by gamma minus T into delta T.
Okay, I have one more answer. Great. Anyone else with it? Any other answer? So after doing the entire chapter, I have to go back to the first class. Okay. So I come back to this class and this is the class where we discuss change in internal energy and then I gave you something to write. Change in internal energy is F by 2 NR delta T It is NCV delta T. I also told you that it does not depend on path. Does anyone remember it? No one remembers it. Great. And it is same for all the processes. It does not depend on the process. That was what we discussed in the first class, that the internal energy is a state variable.
Just now you said it, sir.
Yes, beta? Yes, beta?
So the answer this now, sir.
I'm not able to understand what you are saying. Change in internal energy. I must remind you, after doing so much of hard work for the 3-4 classes, I think I'm back to square one. I just don't understand what should I teach next. Sometimes you get to a point where you forget what to teach. And I am at that juncture where I've forgotten what to tell you now. What should I do next? I'm lost. Was if doing I thought that I have done the entire chapter and I was supposed to wind down the chapter, and I ask you change in internal energy and I get all sorts of great answers. That is absolutely great. Anyways, I have to buck up because
Sir, just now I have shared that formula, sir.
so the change in internal energy for any process is NCV delta T. It does not depend on the process. This is one of the 1,000 times I have told you that, but I hope that one day it will get into your head, and I hope that day comes before your JEE Main ka exam. So delta U is NCV delta T. For this process or for any process, delta U is given by this formula. Now I can write the delta Q for this process. For this process, delta Q will be NC into delta T, where this C will be known as molar specific heat for this process. C will be known as molar specific heat for the process. Every process has a different molar specific heat. We have discussed this and I hope that you remember it. Now, this CV can be written as, so this CV can be written as R upon gamma minus 1. So I can write this as R upon gamma minus 1 into delta theta. Okay, now I don't expect that you will know this, but can anyone tell me what will be the work done in this process? Can anyone tell me what is the work done in this process? Now, how do I remember the work done in this process? My way of remembering it is I will tell you that way. And if you can understand it, it's good. If you don't, well, just remember it in whatever way you feel comfortable. Now, my way of remembering this is this way. Now, once we had done this adiabatic process, we had found out the work done in this adiabatic process, and the work done in this adiabatic process was given by this formula, negative of nr delta T upon gamma minus 1. Now, this adiabatic process was also written in this form, PV raised to the power gamma is equal to constant. Now, once the process was PV raised to the power gamma is constant, we got the work done as minus nR delta T upon gamma minus 1. When the process was PV raised to the power gamma is equal to constant, the work done was minus nR delta T upon gamma minus 1. I hope I have repeated it enough time that you remember. Now what happens here is the process has now become PV raised to the power eta is equal to constant. Where is this gone? The process has now become PV raised to the power eta as constant. Now, can you take some inspiration from that previous one and tell me what will be the process, what will be the work done in this process? When the formula was PV raised to the power gamma is equal to constant, you know the work done. Now you have PV raised to the power eta is constant. Can you tell me the value of work done in this process? Can anyone try? Okay, so the work done in this process can be written as minus N R delta T upon eta minus 1. That is correct. I can now multiply the minus sign and I can write it as NR delta T upon 1 minus eta. Or I can write it as P2 V2 minus P1 V1 upon 1 minus eta. So now I know all the three things, and they can only ask you these three things. Once you know these three things, any process that is given to you in this form can be found out. Now, one more thing they can ask you. Remember, this delta Q is always equal to delta U plus delta W, my dear friends. Now, the last thing that I can ask you is, you can write this delta Q as NC delta T. You can write this as N. Why I'm writing delta? I can write this as N
CV delta T.
NCV delta T, and I can write this as NR delta T upon 1 minus eta. Now, if I just write everything in a different way, NC delta T, NCV can be written as R upon gamma minus 1 into delta T plus NR delta T upon 1 minus eta. And if I cancel the common terms, I can get the molar heat capacity in this process. The molar heat capacity in this process can be found out from this formula, R upon gamma minus 1 plus R upon 1 minus eta, or you can also write it as CV plus 1 minus R upon 1 minus eta. So if you understand adiabatic process, this polytropic process, as you can see, is exact copy of this adiabatic process. The only difference is, in the adiabatic process, you had gamma. Here in this polytropic process, you have eta and not gamma. I will give you 2 minutes to note this down. Okay, then let us move ahead and solve a question based on this. So here comes the question. Question number 1. An ideal monoatomic gas follows a process PV square is equal to constant if the change in temperature is 50 degrees Celsius and number of moles of the gas is 2 moles. Find number 1 delta Q, number 2 delta U, number 3 delta W, and number 4 the molar heat capacity of gas in this process. I will give you 2 minutes. Everyone understands the question? Yes or no? Everyone understands the question?
Yes, sir.
Yes,
2
sir.
minutes you have to give me the answer for this one. Take your time, take a deep breath. Look at this question. Give me the answer.
W is equals to minus 100 R.
Delta U is equal to
150 R.
150 R. Okay.
Delta W is equals to minus 100 R.
Minus 100 R. Delta Q.
Delta Q is equals to 50 R.
And the value of C.
R by 2.
Okay. Good. I think that looks good, but let me solve it. Here, if I compare it with the equation PV raised to the power eta as constant, we just compare it with that equation, my dear friends, what you are going to get? You are going to get the value of eta as 2 as soon as you get it. Well, everything is now clear. Let us first find out the value of delta U. It is N. Value of N is 2 moles into CV. It is given as an ideal monatomic gas. So what is the CV of an ideal monatomic gas?
3 by 2 R, sir.
Huh?
3 by 2 R.
3 by 2
3
R.
by 2 R.
So 3 by 2 R multiplied by the change in temperature is given as 50. As soon as you get it, you get the first answer as delta 150 R. Done. Then you can now find out the value of delta W. The work done in this process can be written as N. N is 2 into R. R is R into delta T. Delta T is 50 degrees divided by 1 minus eta. So it is 1 minus 2 and you get it as minus 100 R. Do we understand this or this has gone above and it's saying bye bye?
Understood, sir.
Once you get the value of this is this plus this. So you will get this as 50 R. Yes or no? Now to calculate the value of C, you can do it in two ways. You can find C as delta Q divided by N into delta T. You can find it out in this way also. So it will be 50 R divided by 2 into 50. You will get it as R. Or you can do it from the formula. R is equal to CV. CV is 3 by 2R plus R upon 1 minus eta. You do it in that way also. You will
Sir.
end up with R by 2. Yes, beta.
Sir.
Yes, bacha.
Okay.
Do we understand this? Yes or no? It has gone above and it's saying bye bye.
Yes, sir.
Bye bye. Bye bye. Huh? Can I give you the
Understood,
next
sir.
question? Yes or no? No,
Yes,
yes.
sir.
So remember,
Yes, sir.
these are the type of questions that you will find in your JEE Main as well as JEE Advanced. NEET, there is a very less chance of these questions coming. Very less chance. Moving on to the next question. Question number 2 or 3, whatever. 5 moles of an ideal diatomic gas undergoes a process where P into T is a constant. If the change in temperature is, let us say, 20 degrees Celsius, you have to find the value of all the 4 quantities. I hope you know what are the 4 quantities: delta Q, delta U, delta W, and the value of C, molar specific heat for this process. And you have 2 minutes to show your talents. Yes, bacha, tell me.
C is equals to 9R by 2.
C is equal to 9R by 2. How did you get it? Yes? How did you get it?
Delta
Huh?
equals to 250 hours.
How did you get it? I asked you that question. How did you get it? How? First, tell me, how did you get it? More than the answer, what I need is the process. I hope it was not akkad bakkad Bombay wo 80 90 pure 100. How did you get it? Yes, tell me fast. Huh?
Delta U equals to NCV delta T.
Okay, so you can find out delta U is equal to NCV delta T. You can find out delta U from here. This is 5. This is diatomic gas. So what is the 7 by 2, right? 7
5
by
by
2.
2, sir. 5,
Oh,
5 by 2,
5
sir.
5 by 2, not 7 by 2. So everyone is awake. 5 by 2 R into
Oh,
change.
7 by 2, sir. 7 by 2, sir. It's diagonal 7 by 2, sir.
Paka?
Okay, sir.
7 by 2 or 5 by 2?
7 by 2, sir. Delta equal to 350 R, sir.
5 by 2 R it is. So it is 250 R. 7 by 2 is CP, not CV. Okay. What about the next one? You found out delta U. Okay, delta U does not depend on the process. So whatever be the process, delta U will be same. What about the rest of the items? How did you get the rest of the items? You have to get the rest of the items from this condition. Now P into T is constant. Either you compare it with the equation of P and T, or what I do is that I compare is that I make this equation into an equation between P and V. Now P into T is constant. Now T can be written as P into V divided by something which is a constant, NR, it is a constant. So I can write this equation like this. Remember, constant could be anything. So I can write this equation as P square into V is a constant. That means I can write it like this: P into V raised to the power half is a constant. Everyone understand what I have done here? So basically what I've done here is I've changed the equation from between pressure and temperature. I have changed it to the equation between pressure and volume. Do we understand this?
Yes, sir.
That means now I know that half, and this half is my nothing but eta. We get this or no?
Yes, sir.
Once I get the value of eta as half, everything becomes very simple. Delta W can be written as N is 5, R is R, change in temperature is 20 degrees Celsius, divided by 1 minus eta, so 1 minus half, and you get your answer. How much you are getting?
200
200
R,
R.
sir.
Well done, 200 R. As soon as you get delta U and delta W, you can write out delta Q. That
450
will
R.
be equal to 450 R. As soon as you get the value of delta Q, you can write C as 450 R
9 R by 2.
divided by N, 5 R. Oh, sorry, 5 not R, 5 into delta T. Delta T is 20. So you will get this as 9 by 2R. If you don't want to find it out from this way, you can find it out from the other way. Everyone understands this. So any question that comes in this category, you can do it in this way. We understand this, yes or no?
Yes, sir.
Well, great. This brings us to a sort of an end of this first law of thermodynamics. We will cover the second law and other things in the next class. But before finishing there, this first law, there are certain limitations of the first law of thermodynamics which are going to be encountered in the second law of thermodynamics. So write the limitations of FLTD. The most important of this limitation is this third point. It does not tell us whether some process is possible or not. I can say this in this way: it does not tell us the direction of process, in which process the direction is happening. First law of thermodynamics does not tell us the direction of process. That means if I put this pen here and this pen drops, what happens? At this point, the pen has potential energy. Now that energy has been converted into sound energy, heat energy, and it got dissipated. Now, according to thermodynamics, law number 1, first law, this process is obviously possible. This process is obviously possible. Potential energy is getting converted into sound, light, heat. The reverse process is also possible. That means if I give heat to this body, if I produce sound, this pen will go up. But we know that this pen is never going to go up if I produce heat and sound over here. That means the first law of thermodynamics It does not tell us in which direction the process is possible. Do we understand this? Yes or no? So it does not tell us which process is possible and which process is not possible. It only tells us that energy will be conserved in that process. It does not tell us which process is possible. So I am speaking and I am losing energy. This process is possible. The reverse process, someone puts words in my mouth and I get energy. Well, you know that process is not possible. But according to first law of thermodynamics, that process is also possible. So if I work out and lose energy, if I'm speaking and losing energy, someone puts words in my mouth, and I would be able to gain energy. That is not possible. That is the limitation of the first law of thermodynamics. So we are coming to a sort of end of first law of thermodynamics. There are one or two things left, which we shall discuss in the next class. In the next class, we will be finishing up this one. And the only thing that will be left would be heat transfer. And it will be a good time to start heat transfer, because once we are doing heat transfer here also, we will be coming and we will be doing something which is same as heat transfer. So that will be all the two things will be going together. So we will do that in the next class. Take care. God bless all of you. Bye bye. Anyone? Any doubt anywhere? Please let me know. Everyone has noted this down?
Yes, sir.
They can ask this question in a NEET exam. They can ask this question in a JEE exam. What is the limitation of first law of thermodynamics? So please note it down. Take care. God bless all of you. Bye bye.